Label likelihood maximization. Adapting iris segmentation models using domain adaptation. Data is almost always the limiting factor for machine learning researchers and engineers. Data is expensive to collect, and it's hard to create well-balanced datasets. A lot of research has gone into changing this either by generating data or providing extremely large-scale datasets. The problem is similar to the chicken and egg dilemma. Data is essential for model development, and great models are essential for improving data collection quality and volume. We approach the problem by using priors to improve model predictions. This makes model self-improvement possible. Our contribution is a general principle for applying priors as well as an implementation for an iris segmentation problem. Datasets are samples of data that are drawn from an underlying distribution. This distribution determines the characteristics of the data and is therefore called its domain. For eye tracking, each setup may define its own domain. For example, a change in lighting conditions may change the general appearance of samples. In a perfect world, one would find a domain for eye tracking that covers all such variations. In reality, however, complete coverage is not realistic due to the complexity of the domain. Therefore, the domains of the model training data and model test data are typically different, and this is known as domain shift. Domain shift can be alleviated by applying techniques that modify the model in some way to adapt it to the new domain. This is called domain adaptation. We perform domain adaptation by generating pseudolabels for unlabeled test data. The base task is semantic segmentation of the iris, which is achieved using an encoder-decoder neural network architecture. The network used is an FCN variant similar in design to DconfNet. The network consists of a number of encoding blocks, an encoded representation, and a corresponding set of decoding blocks. Each block consists of convolutional layers and either pooling or unpooling operations. Pooling indices from the encoder allows spatial information to be passed easily to the decoder. Label likelihood maximization, shortened to LLM, is a method for generating pseudolabels that are used to train a model on data from a new domain. The method uses the current model and a label prior to create pseudolabels and is therefore entirely unsupervised. Regular gradient descent-based training proceeds by generating predictions and calculating the loss to the updated model. With LLM, pseudolabels generation replaces the ground truth label when calculating the loss. Pseudolabel generation is based on a few assumptions. Specifically, it assumes that the model is already at least somewhat competent in making predictions even under domain shift. Additionally, it assumes that the prior distribution of labels can be modeled realistically. For the task of iris segmentation, the prior is a uniform distribution of all valid ellipses drawn from the 224 by 224 output space. The true prior is not known, and the one chosen here is therefore just a model choice, albeit an informed one. This prior defines a manifold in the output space. The starting point is the model prediction. Predictions are assumed to be distributed around the true value according to some distribution. Here we use the normal distribution. LLM optimizes the likelihood of getting a specific prediction by finding the closest manifold point and assuming that to be the true label source. Because the manifold is not linear, predictions are ranked by the distance between prediction and manifold. This represents the model's confidence in the pseudolabel. Experiments. Since LLM is used for adaptation of base models, the following experiments focus on their relative performance. The base model is trained using synthetic data from the Unity Eyes generator. For testing and domain adaptation, a collection of 4 real-world datasets is used, totaling around 300,000 images. The base model is adapted to each dataset separately. The datasets only contain pupil center annotations, which are approximated using the predicted iris sensors. The center is extracted from the segmentation by performing the same LLM procedure on a prediction and then calculating the parameters of the resulting ellipse. This is important because it ensures that no advantage is given to the immediate improvement caused by segmentation post-processing. Results. We use the detection rate as a function of maximum distance error to evaluate the results. Base is the same model on all graphs, while adapted is the individually LLM-adapted model for each dataset. On all but one dataset, a clear relative improvement is present. The last graph shows slightly worse detection rate at low distances and slightly better detection rate at high distances. Some example images show that the models do indeed improve their ability to create realistic iris segmentations for the provided samples. However, it's also clear that the size is not being inferred correctly. Considering the size distributions for the ellipse prior may help alleviate this problem in future studies. Conclusion. The results are significant because LLM provides a considerable relative improvement at no cost. It's free to use because it doesn't require annotated data. And because all models use the same ellipse extraction method for center estimation, the relative improvement must necessarily be caused by improvements to the model itself, and not by post-processing gains. The work presented here suggests many possible paths for future studies. The core takeaway is that model knowledge is important and does make a difference when creating neural network-based eye tracking systems.